Okay, now we're going to look at adapting the limit laws for one-sided limits. The first 6 limit laws that we had before were written as two-sided limits. We were looking at the limit as x approaches a. Now, if you just took those first 6 and just rewrote them and looked at the limit as x approaches a from the right side and the limit as x approaches a from the left side, those would still apply exactly the way they are stated. So it doesn't matter, the sum, the difference, the product, the quotients. Law 7, though, has to be modified because here we're dealing with the fractional exponents. Okay? We have m and n are just positive integers. If we're looking at this function to a fractional exponent, we have to worry if m is going to be an even number, then that means that the denominator of that fraction is even, which means we have an even root, like a square root or a fourth root. So this limit law will just be the limit of the function to the n over m power, but the f of x has to be positive. And we're looking just at x values, though, that are bigger than the a. So we're looking at numbers, if you have a on your number line, we're just looking at values that are to the right of the number line. So in that case, we just want f of x to be greater than or equal to 0 for x is bigger than a. So that's all we need to worry about. And the second one, now we're looking at the limit laws and we're looking at the left side limit. This is just saying now we're looking at a here, but we're looking at values of x smaller than the a. So here, this limit law still applies. The limit of a function to a power is the same as the limit of the function to that same fractional power as long as the f of x is positive when we're talking about x's that are less than the a. So you just have to worry about if it's a left or right side, be sure the function's value exists for those values, those particular x values. Okay, so now let's look at applying a limit law to a piecewise function. Now here's one where it's not going to be a nice, smooth, continuous, connected graph. We've got it in 2 pieces. So the question is, when you're finding the limit and you have a graph in 2 pieces, will there be a limit at that place where that graph breaks? So I'm going to first go ahead and graph this function. The place it's breaking is at x equal to 1. So that's going to be where we're interested in the limit at. Because individually, if you just look at this top equation, this is just the equation y equal negative 2x plus 4. It's just a line. We know the limit at any point will just be that line's value. The bottom one, the square root of x minus 1, it's an algebraic expression. And as long as the x is bigger than or equal to 1, it's going to have a value. So we don't have to worry about x is bigger than 1 there, but we would worry a little bit about 1. And that function won't even exist if the x is smaller than 1. So let's look at the 2 graphs separately. First, always graph the function at the place it's breaking. Put a point for each part at that point. So when x is equal to 1 in the first one, our y value is going to be at 2. So negative 2 plus 4 is 2. So we're going to have the point 1, 2. And now, is that point actually included? Will it be a solid dot or just a circled dot? Because it has less than or equal to, the equal is with it, then that means that that point will be is a part of that graph. And so now we've got a line just for the x's less than or equal to 1. So I'm going to just pick one other x value. I'm going to let x equal to something smaller than or equal to 1. So I'm going to pick x equal to 0, and I'll see that the y value comes out to be 4. So 0, 4, and I've got a point right there. This line, we're just talking about the piece of the line starting at this point 1, 2, and going off to the left. So that's the piece of the line that we're interested in this function f. Now the second one, hopefully you recognize that square root function. You know the square root function, y equals the square root of x. It looks like this. Okay, it's just the top half of a parabola. To graph this one, though, the square root of x minus 1 is just a shift of y equal the square root of x, 1 to the right. So if I just took that function and shifted everything over 1, it would now start down here at 1, 0 and just go over. So drawing that, or you can pick a couple points. I know what it looks like. So now put 1 into that function. 1 into that second function, the y value is going to be 0. And that's going to be this part, just right here. And now let's pick something bigger than 1 to plug in. I'm going to go ahead and plug in something I know is going to have an easy, nice answer. I'm going to pick 5 for my other x. I just want something bigger than 1. The y here, it comes out to be the square root of 4, which is 2. So, okay, so when x is 5, the y value is going to be 2. Okay, and that graph looks like this. Now, the one thing I just didn't do correctly is there isn't an actual point there when x is 1. Because the equal sign was not included with that part, it's going to have a circle there. So I'm going to have a hole here, and then it's going to go on from there. So now this is at x equal to 1. Okay, so that's my piecewise function. Notice if I drop any vertical lines, it always only hits it in one place. It never hits it more than one place. That's why I know that there couldn't have been a dot for both of them at x equal 1, because it wouldn't be a function. A function can't have 2 y values for one x. Okay, so now, looking at that graph, I want to find the limit of the function as x approaches 1 from the left side. That means pick something smaller than the 1 and plug it in. Now, coming from the left side, that means I'm coming this way toward 1. What are my y values? Well, my y values will be points up here on that part of the line. What are the y's approaching? The y's are approaching 2. Whatever the y value is for that point right there. So this limit would just equal to 2. Now let's look at the right side limit. So x approaches 1 from the right side. So now I'm going to be looking at approaching from this direction. So I'm going to be looking at x is bigger than 1. That means the corresponding values on the graph would be up here for the x's that are bigger than 1. And those, as the x gets closer to 1, the y's are getting closer to 0, whatever the y value is for that hole there. So that comes out to be 0. And now if you see the limit of a function and x approaches 1, that means it's a two-sided. That wants to know what's the limit from the left and the right, and for this to exist, they have to be the same. So this limit does not exist because they were different from the left and the right. Okay? So that's what you do with the piecewise function. Now, I didn't actually have to draw the picture first. Notice if I had just looked at the function definition, look at the x value that they're asking you for the limit at. So if I want the limit as x approaches 1, okay, and I'm looking at it from the right side, what I'm going to do is figure out which of these two equations apply for numbers that are bigger than 1. So this means the numbers are bigger than 1. Well, when the numbers are bigger than 1, that means I'm using this rule. F of x is the square root of x minus 1. That's how I would get the y values. So put in the 1 into that one, and I come up with 0. So then if I'm looking for the limit as x approaches 1 from the left side, now I want to look at this and see, okay, I'm looking at just x values that are smaller than 1. Which of the two pieces apply? It would be this one, because the numbers smaller than 1 fit into that set. That means I need to use this to get the y value, y equal negative 2x plus 4. So put your 1 into that, and you come up with the answer of 2. And so you can do it just looking at the equation and figuring out which of the two pieces will these x's actually fall into the set for. Okay, so far, finding the limits analytically, we've always just actually done a direct substitution. We want to look at another problem. The one that's more difficult is when you have a function and the y value doesn't exist. So if we had a function like this first graph, where here's our graph, we've got a hole here, but it goes on up, and the function has a value, but it's not actually on the rest of that other piece, Finding that limit, it's a little more difficult because the limit here isn't actually equal to the y value. The y value is up here. The limit for this function would actually be the y value for that point right there. So the limit's not necessarily the same in this case where we have these holes. So a case here where we have a y value but it's not the same as what the limit would be, or in this other one where we have a function, there's no value there at all, not even anywhere else, you know, in the y values. So in this case, there is a limit. The limit's whatever this y value would be. So whatever that f of, well, it's not f of a because it doesn't exist. So whatever that y value would be the limit, but f of a doesn't even exist, so it's not defined. So how did we handle those kind of situations when we have those equations? So now, two other techniques I want to show you. The first one, if I have a rational function, so the first thing I'm going to do is see, can I evaluate it? Because if it's a rational function, the denominator is not 0, then all I have to do is evaluate. Just substitute it in, and that will give me the limit. But I notice quickly when I put the 2 into that denominator, I get 0 in the denominator. So that means that I can't use the rules that I've used before to find this limit. So what I'm going to do in this case, when you see that you have a denominator that's 0, try factoring and see if you can eliminate what's causing that denominator to be 0. Because if you remember graphing these kind of rational functions, just because the denominator was 0 doesn't mean you had an asymptote. Sometimes it was just a hole in the graph. And if we just have a hole in the graph, like in this case right here, we have in either one of these two problems, if you just have a hole in the graph, the limit's still whatever the y value would be there. So we can actually kind of get rid of our hole by factoring and reducing the fraction down. So the first thing I want to do here is just factor. Well, the first thing I did was try to evaluate. Notice I get 0 in the denominator. Then I'm going to see if I can get rid of that hole. So now the top, if you factor what multiplies to be 8 and you get the minus 6 in the middle, it's going to be x minus 2 and x minus 4. Okay, on the bottom, I recognize the difference of two squares, x minus 2, x plus 2. Notice the common factor. If you remember graphing rational functions, when they have a common factor like that, the top and the bottom, that's what's creating the hole at x equal to 2. That's telling you 2's not in the domain of the function. There won't be a point there. But if we reduce that down, as long as that's not 0, then we would be looking at the function x minus 4 over x plus 2, which is a rational function, but now it has a value at 2. And that value, the value of x minus 4 over x plus 2, will be where that hole occurred. It'll be the y value where that hole was. So just plug in the 2 into the reduced form of this equation. You get negative 2 over 4, or negative 1/2, and that is going to be my limit. That's where that hole occurs, the y value where that hole occurs. So the limit does exist. It's negative 1/2. So it's as simple as getting that 0 in the denominator, reminding yourself to factor the top and the bottom, seeing if you can reduce down that fraction, and that's hiding that hole. It's finding the function that would be the same minus the hole. Okay, so now this next one, it's a little more complicated because you see x minus 1 and there's not really much to factor there. You actually could if you wanted to use square roots, but let me show you another way to look at this one. We see that if we tried to evaluate, we put in x equal 1, we're going to get 0 on the bottom. So we can't just evaluate to get the limit. So what we're going to do is a little trick. It's called multiplying by the conjugate over itself. You used this back when if you did anything with imaginary numbers, what you're doing is you're creating the difference of two squares, and you're going to eliminate radicals that way. You also did it back when you were rationalizing denominators, getting radicals out of the bottom. Okay, so what I'm going to do is look at that part, that expression that has the radical, and I'm going to find its conjugate, which is just changing the sign in the middle. And now I'm going to multiply this fraction by the conjugate over itself, which is just the number 1, right? This is just 1. So all I'm going to be doing is I'm not changing the value of what I started with. I'm just changing the look of it. It still has the same value. So now when I multiply the top together using FOIL, Square root of x times square root of x is just x. The inside and the outside minus square root of x plus square root of x just cancel, and then I'll have minus 1. So that's what creating that difference of two squares is going to do for you. And now on the bottom, now here's where you want to multiply that out. Don't do it. Go ahead and just leave that denominator as a product of two things. If you multiply it out, you're never going to see the next step, which is going to be to notice that the top and the bottom have a common factor. So look at this x minus 1 on the top as a single term. I'm going to take out this x minus 1. Remember, this is x minus 1 times 1 on the top. I'm going to divide the top by x minus 1, divide the bottom by x minus 1. So now this fraction reduces down to the limit of 1 over the square root of x plus 1. Now I'm able to evaluate. So again, it's not a rational function, it's an algebraic function. Just put in your x equal 1, you get 1 over the square root of 1 plus 1, which is just going to be 1/2. And that will be the limit. So that will be the y values the function's approaching as the x is approaching 1. Now if you put that function, square root of x minus 1 over x minus 1 in your calculator and look at where x is 1, you don't actually have a point there, you actually have a hole there in the graph, but the value would be at where the y is 1/2 if you could find that. So these are just two other techniques: factoring and reducing it down when you get that denominator 0, or multiplying by the conjugate over itself. And sometimes that allows you to simplify and end up canceling out that hole, the place where the denominator was 0.